Welcome, physics students. Let's jump right into this explainer. I am so excited to be your tutor today because we're taking thermodynamics and turning it into a foolproof exam masterclass. We're going to break down the exact definitions, laws, and variables you absolutely need to ace your next test, and we'll do it by completely visualizing the physics.
To kick things off, what if I told you that everything you intuitively feel about heat is actually rooted in an old scientific myth? Seriously, early scientists mistakenly thought heat was a literal, physical, invisible fluid that flowed out of hot objects and into cold ones. They called it caloric. I know, it sounds kind of crazy to us now, but for a really long time, the absolute brightest minds in physics believed heat was a liquid you could practically scoop right out of the pores of a material.
Okay, here's our study guide for today. 1. The death of caloric fluid. 2. Heat versus internal energy. 3. The zeroth law. 4. Variables. 5. The first law. And 6. The four processes. Section 1. The death of caloric fluid. Picture this. The year is 1798. A scientist named Benjamin Thompson, also known as Count Rumford, was observing the boring of brass cannons. He noticed that the friction from a dull drill generated just a massive amount of heat, literally enough to boil water. Now, according to that old caloric fluid theory, a sharper drill should have scooped out way more of this invisible heat fluid from the metal's pores. But, well, that wasn't happening. The amount of heat produced depended entirely on the mechanical work done by the horses turning the drill, not how sharp the drill was. This definitively proved heat isn't a flowing liquid at all. That moment brilliantly illustrates a massive historical shift in thermodynamics. We moved away from the outdated caloric fluid model, which, again, viewed heat as an invisible liquid, to the modern view. Count Rumford's experiment was a real game changer because it demonstrated a profound breakthrough. Heat is simply energy converting from one form to another. Specifically, mechanical work was being converted into heat. Heat is just energy in transit. Moving right along to Section 2, heat versus internal energy. Let's define internal energy, which we represent with the letter U. Think of a bulk system, like a container of gas. It's full of molecules just bouncing around. Internal energy is simply the sum of all the random kinetic and potential energies of those microscopic molecules. In a solid material, this energy is mostly molecules vibrating tightly in place, but in a gas, they are freely zipping around and colliding. But here is the absolutely critical part for your exams. It's all about the microscopic disordered motion. If you take that container of gas and put it on a speeding train, the macroscopic kinetic energy of the whole moving container does not increase its internal energy. Internal energy is strictly an internal property of the system's molecules at rest. Now, this next concept is exactly where students get tripped up on tests. Internal energy is what we call a state variable. It's a property that a system physically possesses in a given state, regardless of how it got there. Heat, on the other hand, is energy in transit. It only exists when energy is physically moving between a system and its surroundings because of a temperature difference. So firmly establish this rule in your mind. A gas has internal energy, but it does not have heat. Saying a system contains heat is scientifically meaningless. Section 3, the zeroth law and thermal equilibrium. Let's imagine you have 3 separate systems. The zeroth law states that if system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, then A and B must be in thermal equilibrium with each other. I know, it sounds like simple common sense, right? But this law actually gives us our formal, measurable definition of temperature. It proves that there is a universal property, temperature, that equalizes when systems are in thermal equilibrium. To really visualize thermal equilibrium, let's use a simple analogy. Imagine 2 tanks of water filled to different heights. If you connect them with a horizontal pipe at the bottom, what happens? The water spontaneously flows from the higher tank to the lower tank until the water levels perfectly match. Temperature equalizing between 2 bodies works the exact same way. Heat flows from the hotter level to the colder level until they reach thermal equilibrium, which is where the temperatures are perfectly equal. But whether those systems can actually reach that equilibrium depends entirely on what separates them. We have 2 main types of boundaries to know. An adiabatic wall is completely insulating. It blocks all heat flow, kind of like a perfectly sealed thermos. A diathermic wall, however, is conducting. It allows heat to freely pass through until that thermal equilibrium is finally achieved. All right, Section 4, intensive versus extensive variables.
So, in thermodynamics, macroscopic variables describe the equilibrium state of a system, but they're divided into two distinct camps, and you'll definitely want to memorize this breakdown. Intensive variables, like pressure and temperature, do not depend on the overall size of the system. Extensive variables, like volume, mass, and internal energy, absolutely do depend on the size of the system.
If you ever blank on a test, here is my absolute favorite exam trick to easily classify any variable, the having the system thought experiment. Imagine a room full of gas in equilibrium, and you suddenly drop a wall right down the middle, having the system. Does the temperature drop by half? No, it stays exactly the same, so temperature is intensive. Does the volume drop by half? Yes, so volume is extensive. It's a flawless trick for your problem solving.
Armed with our variables, let's tackle Section 5, the first law of thermodynamics.
The first law of thermodynamics is simply the universal principle of conservation of energy applied to thermodynamic systems. It is defined by the formula delta Q equals delta U plus delta W. In plain English, the heat energy supplied to a system, that's the Q, doesn't just vanish into thin air. It is spent partly on increasing the system's internal energy, the U, and the rest is spent doing mechanical work, the W, on the surrounding environment.
Let's walk through this visually to see exactly how it looks in a classic physics test problem, a gas cylinder with a movable piston. Step 1, you place a flame under the cylinder, adding heat. Step 2, that heat speeds up the gas molecules, increasing their random kinetic motion, which means the internal energy goes up. Step 3, because the gas is now hotter and more energetic, it expands, pushing the heavy piston upwards against the atmosphere. That upward push is the work done by the gas. Conversely, a compression cycle would just be the exact reverse, with external work being done on the gas to push the piston down.
Now, a quick caveat for your exams. For these equations to work out perfectly, we generally assume we're dealing with quasi-static processes. This basically means we imagine the piston moving infinitely slowly, step by microscopic step. This ensures that the gas remains in perfect thermal and mechanical equilibrium with its surroundings at every single stage of the process, which helps us avoid chaotic non-equilibrium states like, say, a sudden explosion.
And finally, Section 6, the 4 thermodynamic processes.
This is a must-know matrix contrasting the 4 main processes. Let's break them down. In an isothermal process, temperature is constant. Since internal energy depends on temperature for an ideal gas, delta U is 0, meaning all heat equals work. In an adiabatic process, the walls are completely insulated, so heat flow is 0. Therefore, any work done directly changes the internal energy. In an isochoric process, volume is locked, so the piston can't move at all. No work is done, so all heat goes directly into changing internal energy. Finally, an isobaric process keeps pressure constant, where work is simply pressure times the change in volume. Seriously, memorize these. As we wrap up, I want to briefly tease the second law of thermodynamics, which you will definitely cover later in your course. The first law says energy is conserved, but the second law shows us that nature severely limits these processes. Heat engines absorb heat to do work, like a classic steam engine, but they can never be 100% efficient. Some energy is always lost. Conversely, refrigerators do the unnatural. They move heat from cold to hot, but it strictly requires external work to make that happen. A perfect engine or a perfect refrigerator simply violates the laws of physics. Let's leave off with a final provocative thought to test what you've learned today. When you rub your palms together on a cold winter day, are you magically summoning caloric fluid out of your hands, or are you doing mechanical work against friction that directly increases the internal energy of your skin? Well, based on everything we've learned from Count Rumford to the first law, you now know for sure it's the latter. You are beautifully demonstrating the conservation of energy. Thanks for joining this explainer. Study hard, and I'll see you next time.